Hello everyone, and welcome to part C of Internal Assessment Review 1 of Data Science. In this extensive session, we are going to cover question 9 through question 18, focusing entirely on the critical stage of data preprocessing. Raw data is ready for analysis. This is often messy, incomplete, or inconsistent. We'll start by defining the five dimensions of data quality, which includes accuracy, completeness, and deliverability, before diving into six specific methods for handling missing values. We'll also explore how to smooth noisy data using binning, how to resolve conflicts during the data integration, and the scaling. Finally, we'll look into the feature selection strategies to optimize our models. There is a lot of technical ground to cover here. So let's get started with question 9 straight away. So hello everyone, welcome back. We are back with part C, which is data preprocessing for feedback analysis. So let's look at the questions. Here comes the question 9, which deals with data quality issues, which are mainly accuracy, completeness, consistency, and we will be looking two more dimensions. In this question, we explore some important issues that affect the quality of student faculty feedback data. Any analysis is only as good as quality of data we feed into the system. So understanding these issues is essential. We start with three primary dimensions, which are accuracy, completeness, and consistency. Then move on to two additional dimensions that are crucial in learning analytics. So let's tackle each one by one. Coming up first, we have the accuracy. Accuracy tells us how correctly the data reflects the real world values. So if the recorded value is far from the truth, all resulting analysis will be misleading. For example, imagine a student accidentally types 950 instead of 95.0 when entering their semester percentage. So this single typing mistake would distort any statistical measure like mean or standard deviation. Another example is logical contradictions inside feedback. A student may give a rating of strongly agree for a course satisfaction, but in the open text comment field, they write something like the course was terrible. I learned nothing. So this contradiction shows that the data is not accurate at representing the true option of that student. So such accuracy errors are common in large scale feedback surveys, and these surely create noise that must be corrected before the analysis part comes in. Second one is completeness. So completeness checks whether each field in the feedback form has been filled. Students often skip questions, sometimes intentionally and sometimes unintentionally. They may leave fields like course ID, year of study, teacher ID, or the age blank. So when such values are missing, we face several problems, which are we cannot group students by department if the department is missing. We cannot compare classes with if the course ID is missing. If many values are missing, the dataset becomes unreliable. So missing values may appear random or may follow patterns. For example, weaker students might skip certain ratings more often. That pattern itself may introduce bias. So, concluding this, completeness is essential to ensure we have full coverage of all the required fields in our feedback. Now, coming upon the third, we have consistency. Consistency ensures that the same information follows the same format everywhere. So, this issue arises when multiple data sets or form uses different conventions. For example, we have dates may be entered at date, month, or year in one entry, and month, date, year in another. And second one, department name may appear as CS in one part of the data set and computer sci or computer science elsewhere. Or the student gender might be recorded as M or slash F in one data set and the full male slash female in another. So these inconsistencies lead to errors during integration, grouping, filtering, merging, and analysis. Before any high-level analytics, we must standardize formats to ensure internal consistency. So let's continue on the fourth one, which is timelessness. Timelessness refers to whether feedback was corrected at the right moment. Uh, we can say that if students are asked to submit feedback months after course completion, the response will be less accurate because students forget details. Their emotional state may also change with time, which affects their opinion. Ideally, feedback should be collected during the course, immediately after the lab session, or right after the semester ends. Um, this is because timely data gives more accurate, reliable, and meaningful insights. And the fifth one is believability, or we can say trustworthiness. Believability measures how trustworthy the data is. For example, a student might spam the feedback from multiple times, or someone might write a script to submit artificial ratings, or a student might submit extremely biased rating, either very high or very low, because of personal frustration. If such entries are not checked, they can distort statistical measures like mean, median, and correlation. Therefore, authentication, identity verification, and anomaly detection help maintain believability. So, in summary, accuracy, completeness, consistency, timeliness, and believability must be ensured before using feedback data for analysis. These steps prevent misleading results and ensure valid interpretations from a given data set. Now, coming upon the question 10, which is handling missing feedback values. In this question, we explore multiple techniques for handling missing values in student feedback data. Missing data is extremely common in surveys, and choosing the right strategy depends on the dataset size, the importance of missing field, and the type of analysis we plan to perform. So let's walk through each method in detail. First one is ignore the tuple or deleting the entire row. The simplest approach is to delete row that contain missing values. However, this method must be used with extreme caution. It is recommended only when the missing field is not important or the missing field is the class label in the supervised learning task. But if in case many rows have missing values, deletion may improve 50% or more of the data set. This results in loss of information and weakens the statistical power of the analysis. So deletion is rarely preferred method. Second one is filling it manually. So this involves human expert inspecting each incomplete record and manually filling in the missing values. But it has some limitations. This works only for tiny data sets or important or sensitive data sets requiring human judgment. But manual filling is impossible for real academic data sets with thousands of feedback responses. Third one is filling with global constant. In this, we replace all missing values with a special constant such as unknown, missing, not applicable, or numeric constants like 0 or -1. So the one advantage of this method is that this approach is easy and ensures uniformity. However, is that a major drawback? If an algorithm treats -1 as a meaningful value, it may distort results. Therefore, this method is very suited for categorically or which we can say non-numeric data. In the fourth one we have mean, median, or mode imputation. This is most common method. So for numeric fields, use mean or median of the available values. For categorical data, we use mode, which is the most frequent category. This method is simple and effective for large data sets, but on the other hand, it reduces variability. All missing values get converted to the same number, which makes the dataset slightly smoother than the reality. Now, coming upon the fifth one, which is class-specific imputation. This improves upon global imputation by using subgroup information. For example, if a CS student misses a rating, fill it using the average rating of other CS student, not the entire college. Similarly, if a third year student feedback is missing, we must use the average of other third year students, not of the whole college. So this method prevents subgroup patterns and gives more realistic imputations. Now coming up on the sixth one, which is most probable value, which is prediction based imputation. This is most advanced and accurate method. So in we build a model such as regression, KNN, or decision tree to predict what missing value should be based on. It should be based on the students' other responses, their department, their academic year, their CGP, and so on. This method requires computation but produces the best quality imputations. So all of the above six methods offer a complete toolkit for handling missing feedback values in any academic data set. Now coming upon the next question, which is question 11, handling smoothing ratings and detecting outliers. So this question focuses on reducing noise in the data using binning and identifying outliers using several statistical methods. So in part A, we use smoothing using bin means with bin depth is equals to 3. We take the sorted data, sorted feedback ratings, for example, 13, 15, 16, 16, 19, 20, 21, 22. We divide the ratings into bins of equal depth, uh, each 3 value each, with bin 1, 13, 15, 16, bin 2, 16, 19, 20, bin 3, 20, 21, and 22. Now, in the second step, we compute mean of each bin. So, the mean of bin 1 would be 13 plus 15 plus 16 by 3, which would be approx 14.67. Similarly, mean of bin 2 would be 18.33 and mean of bin 3 would be 21. Finally, we replace every value in each bin with its corresponding bin mean. This smooths our sudden jump and reduces random noise in the data. Now, coming upon part B, detecting outliers. We use three widely accepted methods, and first one is box plot method or the IQR method. We compute Q1, Q3, and the IQR, which is Q3 minus Q1. Outliers are the values that are below Q1 minus 1.5 times IQR or which are above Q3 plus 1.5 times IQR. This method is specifically effective for skewed data since it ignores extreme values. Second one is Z-score method. So the formula of Z-score is value minus mean upon standard deviation. A value with Z-score greater than 3 or Z-score less than minus 3 is extremely unlikely in normal distribution and is considered as an outlier. Third one is scatter plot. We visualize all values on a scatter plot. Any point that lies far from the main cluster is flagged as an outlier that we can easily visualize in the graph. Visual inspection is powerful when patterns are nonlinear. Now, coming upon part 3, which is other smoothing methods. Three additional smoothing methods include medians. In bin medians, we replace each bin with its median, better when bin contains outliers. Bin boundaries. In bin boundaries, we replace values with the minimum or maximum of the bin. And the third one is fit a regression line or curve to the data and use predicted values to smooth fun punctuations. So these smoothing and outlier detection techniques are essential for preparing feedback data for further analysis or modeling on a student feedback data. Now, coming upon the question 12, which deals with data integration, which is schema, redundancy, and conflict resolution. In academic institution, feedback data often comes from multiple sources such as exam systems, library systems, placement database, student information system. So before analysis, these data must be merged. Let's break down the process. First one is schema integration and the entity identification problem. Different systems may refer to the same attribute using different names. For example, student underscore ID versus the roll number. And other may be department underscore name versus DEPT, which is its abbreviation. So we solve this using metadata analysis, where we map attributes from the different systems to a common unified schema. Identity identification ensures that multiple entries referring to the same student are merged into one correct record. Now, second one is handling redundant data. So let's talk about how a redundancy arises. So redundancy arises when a student appears twice because of name spelling variations. Derived attributes like age and DOB are both stored, or multiple systems store copies of the same values. And to remove this redundancy, for categorical data, we use chi-square test. For numerical data, we use Pearson correlation. So if correlation is equals to 1.0, one attribute is redundant. And removing redundant data reduces storage and improves processing efficiency. Now let's talk about resolving data value conflicts. In this, two systems may store the same attribute with different values. For example, one database stores marks out of 100, another stores out of CGPA. One data has an old address, another has an updated one. We solve these type of conflicts using standardized rules, converting all values to a common scale, or by trust rules, where one system, for example, registration office, is considered as the authoritative sources. So all these steps which we have discussed just now ensures clean, organized, and reliable integrated data for our analytics. Yeah. So next up, we have question 13, in which we'll be discussing detailed explanation of normalized method. This question explains four normalization techniques that scale numerical data into comparable ranges. First one, we have min-max normalization. Its formula is V minus minimum upon maximum minus minimum. So its advantages are it maps values to a fixed range, usually in the closed interval of 0 to 1, and it preserves the original distribution shape. Few of its disadvantages are it is extremely sensible to outliers, and and a single extreme value can compress an entire range. Next up, we have Z-score normalization. Its formula is V minus mean upon standard deviation. Its advantages includes produces values with mean 0 and standard deviation 1, and it is better than the min minus max for handling outliers. In the third one, we have Z-score normalization using mean absolute deviation, which is standardization. Instead of standard deviation, we use MAD, which is average upon V minus mean of modulus. We use this because this is more robust scaling since it reduces the effect of extreme values. In the fourth one, we have decimal scaling. Its formula is V dash is equals to V upon 10 ki power j, where j is chosen so that the maximum of V mod dash is less than 1. So, for example, if the maximum value is 986, we divide by 1000. This method shifts the decimal to reduce the magnitude uniformly. So Next up, we have question number 14, in which we would be normalizing faculty workload values. This question applies the four normalization methods to workload values. Here we have the data sets 200, 300, 400, 600, and 1000. Each normalization methods transform them differently. Min-max maps them between 0 and 1. Z-score converts them to standardized units. MAD-based Z-scores make them more robust. And in the end, decimal scaling shift decimal places based on the magnitude. Here, each method serves as a different analytical objective. So we can easily see how we have carried out the calculation for the each discussed method. Now, coming upon the question 15, where we would be normalizing the feedback values of 35. Here we have normalized the value 35 using the same techniques which we just discussed. From Let's discuss here again for the value 35. First one is min-max normalization. It requires data sets minimum and maximum values, and it produces a value between 0 and 1. In the second up, we have z-score normalization. Its formula we can see its formula here, and it requires mean and standard deviation. It actually says out how many standard deviations 35 lies from the mean. And in the third one, from the decimal scaling, it divides 35 by 10 to the power j. Now, here comes the tricky part. We are going to choose which method is the best method out of the four available ones. If we use min max when working with bounded scales like 1 to 100, and we use z scores when comparing across different scales or when we are handling the outliers. Now let's tackle question number 16. This question uses age and productivity data. Here we use z-score normalization and Pearson correlation. Let's do part A, which is z-score normalization. Here we compute for each value minus mean upon standard deviation. This puts both attributes on the same scale. Now coming upon part B, we solve covariance and correlation. So covariance means the direction of the correlation standardize this between -1 and +1. And what does this -1 and +1 symbolizes? If correlation is positive, productivity increases with age. And if it is negative, productivity decreases as the age increases. And one thing more, correlation also tells the strength of the relationship. Now, coming upon the question 16, where we are partitioning scores into bins. We have 12 evaluation scores to partition using three methods. These scores are 5, 10, 11, 13, 15, 35, 50, 55, 72, 92, 204, and 215. Coming upon, let's do this with the available methods. First one, we have equal frequency partitioning. Here, each bin has equal number of values with 12 values and 3 bins. Each bin has 4 values. Just a minute. Yeah. Now, coming upon second, equal with partitioning, we divide entire range 215 minus 5, which is 210, comes out to be our range with into equal width intervals. By this, each bin covers the same numeric width. Now, coming upon part C, which is clustering. We use clustering algorithms like k-means to form groups based on similarity. Bins are formed dynamically based on the patterns rather than the fixed intervals. Now, coming upon the question 18, which is feature selection, forward selection, backward selection, and hybrid. In this question, we summarize the feature selection techniques, or we can say the strategies. In the forward selection, which we can clearly see here in the flow chart, It starts with zero attributes, starts with zero attributes or no features, add the attributes that increases the model accuracy the most, and it does repeat until no further improvement occurs. Now, in the backward elimination, it starts with all values. Remove the attributes whose removal least affects accuracy. Now, then repeat until removing more attributes harms the model. And now the third part, which combines both. Add attributes like forward selection. After each addition, check if any existing attributes has become redundant and remove such attributes. This yields an effective and optimal attribute set. Now here we are done with part C. In the next video, we will be winding up the internal assessment one, part 4, which is left, and we will be done with the internal assessment one question paper. Thank you. And that brings us to the end of part C. We have now covered the essential toolkit for turning raw, messy data into a clean, reliable data set. We have learned that simply deleting row with missing value is rarely the best option, and the techniques like class-specific imputation offer much better accuracy. We have also clarified the difference between forward selection and backward elimination in feature engineering, and why normalization is crucial before comparing attributes with different scales. Remember, whether you are using min-max scaling or detecting outliers with IQR method, the goal is always to improve the quality of downstream analysis. So review these formulas and methods carefully. Next up, we'll discuss how to string these matrix datasets efficiently in our final part of our assessment, which is part D.